Can you hear me?
Yes.
Is that a yes? No? Can you? I'm not sure. I'm trying to adjust things. Yes. Thank you. Sorry about that. Multiple windows open where multiple mics. You can never figure out where it is. Let's see. So let's just give everybody a couple more minutes and we'll start. We'll start in 2 minutes. All right, let's get going on this thing. We'll try to wrap up the overview of the packets today. So the primary thing I'd like to cover is basically packets 5 through 22 and make sure we're on the same page in terms of basics of what's being covered. Again, next week on Tuesday, we'll also cover the final from 2019 and the final from 2020. And then if there are any other questions, it's an open mic time. It's good to bring all your questions and we can have Q&A all of next week on any topics you like related to the class. So the issue with packet number 5, which is what we're dealing with right now, is a deeper look at continuum mechanics. The primary interest, of course, there, looking first at the notes, if you look at chapter 5, is the ideas of deformation and strain in particular, the green Kirchhoff-Saint-Venant constitutive law, which requires the Green-Lagrange strain, the deformation gradient, the density. Of course, you don't have to derive these all from scratch or anything of that sort, but it's good to understand the flow of exactly how these concepts fit together for the deformation and strain of materials, in particular at finite deformations. I would suggest that, those of you that want to go deeper into this should really take the class MEC or ME 287. It's also an undergraduate class called ME 185. And it's more or less the same. It's just cross-listed in either case. That class provides really a deep foundation in continuum mechanics for those of you that want to get deeper into the concepts of flow, conservation laws, and so forth. At any rate, the purpose of chapter 5 was to give you a taste of everything that has to do with continuum mechanics. In particular, the main topics, of course, are deformation, stress, thermodynamics, and then constitutive laws. So let's look at packet number 5 a little bit more closely, and then we'll come back to the notes right now. So in packet number 5, the main topic of interest is that we have some kind of arbitrary blob, and that arbitrary blob could have come out of a 3D printer nozzle. So if there was a nozzle and this stuff happened to be released, the idea is how is this thing going to deform after a given period of time, and then when it splats onto a surface. So if you really wanted to do a deep analysis that goes beyond just simply treating it as a rigid body, as we did in the very first project, you would really want to go through this whole concept of deformation and strain. And I can assure you it's a rich and beautiful topic, but certainly one that is quite time consuming. If you were to write a 3-dimensional finite element code for a problem like this, you would have to attach a mesh to this kind of an object and then basically track how the mesh deforms as the body is starting to undergo extremely large deformations. That requires some relatively sophisticated numerical techniques that have to do with arbitrary Lagrangian methods. For those of you that may have taken a class in finite elements like 280A, there's a subsequent class called 280B where they delve deeply into these kinds of topics. So for those of you that might be interested in numerical analysis of these types of systems, the classes 280A and 280B are the ones that really bring all of this home. But again, topics that require some deep analysis in terms of continuum methods and so forth. And that's really not the subject of this class, but certainly is of importance. So the basic idea here is that we have something in the distinguishing features between the current deformation configuration and the reference configuration. So this is, of course, the ref, and this is the current configuration. And then based upon this, we construct everything afterwards, that x minus big X is equal to u, then subsequently the gradient of x minus the gradient of big X equals to the gradient of u, and depending upon what we take the gradient with respect to, for example, with respect to big X, we then get the fundamental relationship that says this quantity, which we anoint with the name f for the deformation gradient, minus the identity, because this is x with respect to itself, is equal to the gradient of the displacement. And from there, everything goes forward. We start to develop all kinds of different measures of stress and strain. Of course, the one that's most important to us is the Green-Lagrange strain. And the Green-Lagrange strain is 1/2 ft dotted with f minus 1. And that, of course, is a strain measure that collapses to the classical small strains measure, which is the one we've used in undergraduate analyses, as the deformation gradient tends towards the identity, meaning that the deformations between the deformed configuration and the current or in the reference configuration start to get so close that they're almost on top of each other. In that case, the deformations are considered to be infinitesimally small. And from there, we develop all kinds of classical linear elastic behavior. So again, I can't go through everything in the review, but simply what I would say is the key features of the things I would like you to be able to have mastered are the concept of X, the concept of big X, the concept of the deformation gradient, the concept of the Green-Lagrange strain, the concept of initial density, current density, and the Jacobian of the deformation gradient. So you should feel comfortable with these quantities and how they're interrelated. And we had some classical examples with some relatively easy things to encode in project number 2, which gave you just basic deformation states of objects. Now, of course, there are many manufacturing systems that will produce different types of deformations. Some classical ones, of course, are things like extrusion, where we take an object that starts like this, we put it through some kind of a hole or orifice, you push it through, and then you start to produce long, thin wires. Of course, depending upon how we construct the deformation gradient F, we can reproduce this kind of a deformation of a manufacturing process, or if it happens to be something like compaction, where we take an object, we put it in a very strong container, and then we basically squish this guy from all different directions, and we produce then smaller, more dense ingots. Of course, that also is dictated by certain values of the deformation gradient. And of course, we could produce many others depending upon what kind of system we want to mimic. But ultimately, if we want to really do a deep dive and an analysis of any kind of object that is undergoing some kind of loading on the boundary, some type of deformation and so forth, you would have to really solve the divergence of sigma plus F equals rho V dot. And if that's the case, this requires, unfortunately, FEM for almost any kind of case with a complicated geometry. So if you have, however, sometimes geometries that are relatively regular, perhaps they're some kind of an analysis of a box or some kind of an ingot, finite difference time domain methods certainly suffice and are actually faster. So oftentimes, if the deformations are small and the geometries are regular, these types of methods are preferred, and there are a variety of different reasons why, but primarily the meshes don't get distorted. And if you have objects where things start to change in their shapes, for example, change in different configurations, the finite element method is uniquely adaptable to this kind of a configuration, but costs a lot more than the finite difference method. So it just depends upon really what you're after. You'll find that finite difference time domain methods are usually used for linearized or small deformation problems, wave propagation, things where the body doesn't distort a lot. But for manufacturing, almost universally, it's finite elements. So I can't extol the finite element enough. It was absolutely the game changer in the 1960s that really opened up the entire world to all kinds of digital technologies. And many of you, if you had logged in, and I don't know how many of you logged into the Boeing discussion yesterday, I had the CTO of Boeing that gave a presentation on all the things that they're doing. And I have to say, it was almost like it was the 201 class. I mean, every single thing that they were discussing was every single thing that we're doing in this class. So that's definitely worthwhile looking at the aircraft industry and how they're really making great strides. They've had, of course, horrific problems with their 737 and other types of air disasters, some due to human error, some due to just sheer negligence. But generally, I mean, everybody tries to correct iteration after iteration. So certainly it's worthwhile looking at. The aircraft business has always been at the forefront of using these kinds of technologies. At any rate, the main issue that, other than the, so-called mechanical side of problems, which are the ones that are here, are also to understand the thermodynamics. And the thermodynamics, of course, are given by the following type of problem, where we have the density, the stored energy in the system, the stress, the inner product with that, with the velocity, minus the divergence of the heat flow, plus rho z. That is the classical equation that we care about. Of course, that's in the current configuration. And the reference configuration, it's rho 0, W dot, S times E dot, And then, of course, we have the divergence with respect to big X of Q0 plus rho 0 times Z. Again, that's in the reference configuration, right? So depending upon what configuration might be easier to solve the problem in, they're certainly interchangeable. These are not approximations. These things are really identical, these two types of formulations, except just one is holding over the reference configuration, and then one is holding in the deformed configuration, which is shown here. So depends upon, what is the type of problem that's being solved. You'll see in many commercial codes, they may formulate the problem in this configuration or this, or actually mix the two and oscillate back and forth depending upon, what is more advantageous computationally. At any rate, the main point I want to get across is that you should feel comfortable with these two types of configurations. And you'll see in the previous finals that we go very carefully and in depth into this with several of the problems. But again, if you've done the projects, those problems are relatively straightforward. So I'll go very briefly then also into the thermo packet, which again is just exactly reiterating what I'm showing you here. Again, main issues there are simply things like stress and strain. So stress, strain, that's packets 5 and packet 6. And then thermodynamics, packet number 7. And again, the main ideas, again, from packet 6 that are important, I think, are, for example, Nansen's formula. So Nansen, how do you actually use it? What is the concept of the second Piola-Kirchhoff stress? The reference configuration relationship between, sigma and S. That, of course, is that sigma is equal to 1 over J Fs, Ft. That's pretty dang important. Other than that, I mean, all the rest are things that, I wouldn't expect you to know, from the top of your head, but this one should be in burned memory to understand exactly the relationship between the two. I would be prepared also to think about the eigenvalues of the stress matrix to understand exactly how to do that and what they mean. Those, of course, are the classical ideas of principal stress. In packet number 7, the main idea is flow of energy at time t, then plus some work done from state 1 to 2, so call this state 1, and then it's time t plus delta t. We have then some new state of energy, so we call this energy here, and if we subtract the difference between the energy at state t plus delta t and add to that the work energy equation, we get the classical equation that says that it is the time derivative of the potential energy I plus the time derivative of the kinetic energy with respect to t is equal to the time derivative of the work done from state 1 to state 2. And of course, this rascal here is nothing more than the power. At that point, we decompose the power into many different components, the mechanical part, the heat part, the source part, and we derived, of course, the first law of thermodynamics, FLT, which is the one that we have right here. Hyper important. I really can't stress enough that equation. Knowing that in the life as an engineer has proven to be quite useful for solving a variety of problems. Of course, it itself is virtually impossible to solve in closed form. So we oftentimes use simplifications based upon engineering judgment, when to neglect, conduction, when to neglect the sources, when to neglect the power terms, the stress power. That depends upon, the circumstances of the problem. One example I gave you was the problem of lasers, where we basically had the input of a laser and how we go from the general first law of thermodynamics down to a relatively simple differential equation that tells us here how to solve the heat conduction problem. So you can go from the heat conduction problem, there is a linear line all the way down from the first law of thermodynamics until you make certain approximations that you can get an equation that's relatively easy to solve numerically that happens to do, of course, with lasers. And oftentimes in laser analyses, we don't care about the stress power and the deformations are relatively small. Therefore, we only have storage of energy terms that are only thermally based. We don't have mechanical energy storage. So the problem, of course, becomes somewhat easier. Okay, packet number 8. Basically, again, their material laws. The main issue that I would like for you to remember and to feel comfortable with are, for example, how do we get to the classical linear elastic stress-strain relationship that says that we have an elasticity tensor times the linearly elastic strain? How do we turn this into an isotropic material? We have the bulk modulus, the shear modulus, the Young's modulus, the Poisson ratio, all of those relationships. The idea of pressure, which is simply the stress divided by 3, plus minus, depending upon who's defining. Some people define it as minus, some people define it as plus. I just call it simply the trace of the stress. Then, of course, we have the main concept here, which is the deviatoric part, which is taking the stress minus the trace of the stress tensor over 3 projected onto the identity. This quantity here, of course, is important for failure analysis and then also for deformation of materials because it basically controls the distortion of the solid. So you should feel comfortable with these main concepts here from linearized elasticity. And again, they start directly from the first law of thermodynamics, ignoring heat terms. And then after that, it's all pro forma and basically paint by the numbers. It's a very clean and beautiful topic, linearized elasticity. And of course, extraordinarily useful, especially for example, the aircraft industry, because again, planes don't go through gigantic deformations. For design analyses, linear elastic analysis is absolutely the go-to type of tool. So at any rate, you should feel comfortable with these ideas of basically stress, strain, the constitutive laws, the quantities that have to do with things like the bulk modulus, the shear modulus, and so forth. So you should feel comfortable with almost all of those. You don't have to sweat over the elastic symmetry stuff. We didn't cover that in depth. So you can, of course, ignore that type of analysis in the problem. But for those of you that are in material science in particular, it's also critical, the concepts of material failure and how we actually calibrate material failure on page number 8 of that packet, with basically starting with a simple one-dimensional stress-strain relationship or law, or a shear type of test, how we can construct the von Mises criteria. That thing is, of course, central to almost everything we do in terms of failure analysis. Of course, almost all of the subsequent failure analyses that are a little bit more, complex, build upon this sort of building block of the von Mises criteria, which is shown here on page 9 and also on page 8. So again, depending upon how you've seen it portrayed as an undergraduate, the von Mises criteria, the formula for it can really be boiled down into a much simpler case here, which simply says that the norm of the deviatoric stress has to be less than 2/3 sigma 0, where sigma 0 comes from a simple one-dimensional test. So that's important because then you don't have to remember all that crazy crap from all the formulas. Of course, after a while you can't forget them, but generally speaking, the formulas there can be boiled down to something pretty straightforward in this regard. So that's packet number 7, 8, 9 is then Maxwell. And again, for Maxwell's equations, also a supremely useful tool. For this class, however, our primary interest was in Joule heating. So you can, of course, go through the analyses and derive Maxwell's equations, which again are absolutely useful for our modern world. Cell phones, circuit boards, laptops, all designed with Maxwell's equations. where basically you take the curl of the electric field that's related to the time derivative change of the magnetic field, then the curl of the magnetic field primal value H is equal to the partial derivative of the electrical flow plus the flow of current. Now, these two equations form the basis of almost everything in electromagnetism. And in fact, things like generators, electric motors, etc., those are all driven by knowledge of these equations. Any kind of, battery analysis, electrical charging, things of that sort, it's all Maxwell's equations. However, for our purposes in manufacturing, really what we're after is when some kind of a material is subjected to some type of flow of current, that we would like to know how hot it gets. And how hot it gets is basically going to be given by the product of the current field with the electric field. That is in fact shown to be equal to the amount of heat that gets dumped into the material through processing. So that becomes an extraordinarily useful tool, resistive heating, because of course then we can melt materials depending upon how much current we pump into them. So oftentimes in the first law of thermodynamics, we'll then see the equation that looks something like this. You take the stress, you take the gradient of the velocity, you take the divergence of the heat conduction, and then you have some kind of an absorption constant times the current field times the electric field. So of course that's critical. And this then becomes the term that you can actually control. So you had a pretty, meaty project number 3, lots of equations, although at the end it's derived many terms there. But the equation itself is relatively straightforward to solve, because ultimately, when you take a problem like the one you had with the conduction and the plunger and the electrical flow flowing through this thing, at the end, you'll end up getting, through many simplifications, an equation for the average temperature inside that solid is equal to some kind of a function of theta. And of course, then you really can solve this using a standard finite difference technique. You take theta minus t delta t is equal to f of theta of t. And then basically the idea then is theta of t plus delta t is equal to theta of t plus delta t times f of theta, and you're off to the races. Of course, to get to whatever this monster is in your assignment, I derived it for you in the notes. I mean, in the actual assignment itself, F can be something, horrifically complicated, but at the end of the day, you're faced with only solving an ODE for the value of the temperature inside of this blob versus the nightmarish problem of taking this thing, discretizing it with some type of a finite element method. So you could, of course, do that and then put a grid on this rascal and then basically solve this equation where you have all of the different pieces of material that are basically then going to be heated up through the partial solving of that partial differential equation. Not an easy task, I have to say. I mean, the problem is relatively, beastly. However, again, first law of thermodynamics can be reduced, and you can get a pretty good approximate model that you can get away with for most design analyses instead of going after this monster. Now, the way I usually use these kinds of approximations is I will use these for design methods because they're easy to solve, and I'll slap on a genetic algorithm and let it go and pound that thing until it gets close to the parameters that I need. And then when I want to do some refined analyses, I go into this thing and then simply solve it accordingly. So it really is a two-pronged attack. And once you feel good about that and feel comfortable with it, you should be able to feel, a little bit more empowered in terms of the methods of analyses. I think one thing that is always a dilemma in modern engineering analysis is we have all of these incredible numerical tools, but no one really knows exactly what's going on inside of those things. And in fact, because they were all written 30, 40 years ago, there's sort of a legacy issue there that it starts to become a lost amount of knowledge, and the codes are basically these black boxes that no one has quite an idea of understanding. So hopefully this class gives you a little bit more of an analysis background to be able to deal with that stuff. So your packet number 12 was basically geared towards trying to show you how all of these things are integrated together so that you can solve a pretty complex numerical problem that came from an industrial project I had once almost 15 years ago from the Siemens Corporation, where they were trying to make turbine blades with these kinds of methods. And again, that's something that I think would be rather useful to understand. But again, I get it with the comments that I got that, boy, this is a lot of equations, but at the end, it really does boil down to something rather beautiful and simple. And it really does deliver methods that, or at least analyses that are quite useful. Now, packet number 13 was then just trying to give you a foray into how you solve spatial gradients of types of problems. And of course, a problem like the one that we had previously, where we had the compaction problem, clearly it's not going to be entirely okay to say that this just has a single value of the temperature inside of here. It's of course going to vary along the length of these kinds of bars. So what I did is I basically said, look, let's look at a one-dimensional problem that's equivalent to this, just to get an idea of exactly how this works. So it's important to understand finite differences. I think you should expect to have something like that on the final, to be able to formulate these kinds of things and understand exactly what the basics are of exactly how these things heat up and how we discretize them in time. Packet number 14 basically then goes one step further. It shows you exactly how you can solve coupled problems. And since we had looked at the Maxwell's equations, that's of course a reduced version, the first law of thermodynamics and stress, I decided to concoct a problem where we would mix all the three together so you can get an idea of how multi-physical problems work. In particular, the concepts of voltage, which are pretty commonly used in electrical engineering, as a technique by which people can determine whether something has a voltage potential. Electrical engineers primarily have used these kinds of things, because their design is mainly in storage of energy. Voltage is not commonly used, for example, in continuum electrodynamics, because the objective usually isn't voltage. But if you're a battery person or an electrical engineer that's trying to worry about transformers, steppers, things like this, the concept of what the voltage is important. And of course, the voltage has a relationship to the electric field. If you take the gradient of the voltage with respect to X, you get the electric field that actually acts on a body. So you can always determine the voltage from the electrical field and vice versa by simply integrating or differentiating accordingly. At any rate, the main point of that topic was to simply formulate the problem in terms of a partial differential equation for the temperature along the length of the bar. So the idea is that we were going to set up a one-dimensional problem, discretize it with finite difference nodes, and then set it up as a spreadsheet calculation after you apply the boundary conditions. So then you would just basically get then the values of the temperature at the nodes at time t plus delta t, and then the updates that basically update the values in time. So again, that was packet number 14. Which again was more of the multi-physical flavor of the analyses. Packet 15, again, more deeply into it, and of course an adjoining project where we basically worked out a problem for a laser, again using exactly the same physical equations, except that of course the laser is applied on the surface area, and it was a three-dimensional problem, which of course is something that is inevitably you're going to encounter as a practicing engineer. And Brian and I had, debated this for quite some time, whether to give you, no three-dimensional versus three-dimensional. But at the end, I think we were both in agreement that a 3D problem is somewhat a necessary thing to have encountered, especially if you have to discretize it and formulate it. So it's important to understand exactly what goes into the nuts and bolts of a three-dimensional heat transfer problem in this case. But of course, these kinds of methods can be used for a variety of different techniques. But there, you should expect some questions along those lines. Packet number 16 basically goes through a simple model of a laser. So basically, if we treated this as one big lumped mass, could we come up with one of those little nice ODE type problems to set this up as a single problem, much like our compaction problem? We have a single value of the temperature in the middle. The answer is, of course, yes, you can do that. The degree of accuracy, of course, is questionable, but again, for qualitative or design purposes, when you want to test many possible configurations of how much laser input, what should the base properties be, how high should you make the fan, how much energy is going to be radiated out. Oftentimes, these kinds of analyses are preferred, at least to do multiple or many thousands of these kinds of configurations. So packet number 16 gives you a taste of that. Packet 15 is 3D finite difference time domain. Packet number 16, of course, are simplified analyses. Finally, the idea of, in packet number 17 was to just give you a much more in-depth analysis of exactly how you encode these finite difference, these 3D finite difference techniques, and apply it directly to a laser problem. So on packet number 17, we apply the finite difference time domain method to a laser problem. And again, the problems are almost always, it's kind of the same broken record. We set up the first law of thermodynamics. We make some approximations. We get it into tractable form. We then apply the boundary conditions onto the surfaces, depending upon what they are. We apply approximations to the derivatives, in this case, of course, in 3 dimensions. And then we set this thing up with all of the boundary conditions. And at the end, we get a spreadsheet calculation that says, look, the values at the nodes at time t plus delta t, the value of the nodes at time t, and the updates, and then we're basically able to step the problem forward in time. So again, another rather beautiful and succinct way of doing it that is, of course, become very popular in the heat transfer business. Packet number 18, just go here quickly, moment. So packet number 18 was essentially the theory. So packet 18 was a theory of how you go from classical electrodynamics or electromagnetism to the concepts of flow of light and energy. And again, there are many approximations that you can take whenever you're considering radiation, how it propagates as a wave. If you do the analyses appropriately, that you have the frequency of light is extremely fast and the wavelength is extremely small, you can start to make all kinds of approximations that treat these things by so-called ray theory. So ray theory is one of those methods by which that in the special case where the type of electromagnetic radiation is relatively fast oscillating and extremely small, it turns out that the electromagnetic radiation behaves like a ray, just like we think about any kind of ray of light and so forth. So this provides an extremely useful technique by which we can track the propagation of lasers, light, optics, and things of that sort. But packet number 18, which I don't expect you to go through because we didn't spend any time on it, that it's the theory of this, is just to show you exactly how you can connect classical electromagnetism to the propagation of waves and rays and so forth. I would suggest that if you're interested in such a thing, take the class 290G in the Department of Mechanical Engineering, or potentially the class EECS 100, and I believe it's 10 or 115, the number escapes me right now, but it gives you basically the theories behind all of these different electromagnetic formulations. Packet number 19 is the physics of diffusion. So packet number 19, we didn't cover it, did not cover, but it is a rather important topic in the Bay Area, which is essentially chemical vapor deposition, or CVD. The basic idea is we can set up governing equations for how these materials are built up layer by layer by layer by diffusive type methods, using masks, and then also using lasers in tandem with masks. So integrated circuits, basically, they start out usually with some kind of a silicon substrate. They put then some kind of a pattern or a mask onto the surface. They make all kinds of different configurations of these surfaces and so forth. And the basic idea there is that by taking a series of masks and a series of laser applications, you can start to build up rather incredible electronic circuit boards and structures by simply building onto a silicon substrate. You can use intermittently lasers and layers of epitaxial gas, which basically builds up these layers. So these are gas. Typically, these processes will have almost 50 different cycles, meaning that if you start out with a blank piece of material and you want to build some kind of a complicated circuit board, you probably need to do 50 cycles of layers of stuff, laser, and do this about 50 times to build up some kind of a layer of a circuit board that is of some value. This is, of course, why it's hyper important to have clean rooms, to have all kinds of stuff where you don't have any impurities, because any impurity, of course, will screw up this process and then everything else is gone. So quality control in these methods are important. So the governing equations for these are almost identical to the first law of thermodynamics. You end up getting a differential equation that in a formal sense is exactly the same. And you can, of course, then apply the same kind of numerical techniques for finite difference discretization in time and in space. And if you do this properly, you can set this up as a type of spreadsheet calculation as well. So again, not covered in this class, but again, a topic of pretty high importance. So the last topic that was, or sorry, not the very last, but close to the last, the idea of the optimization of materials, and packet number 20 basically set up the problem of taking small heterogeneous blobs of material. So for example, what we sometimes refer to as representative volume elements, and ascertaining if we know the volume fraction of phase 1 and we know the volume fraction of phase 2, which adds up to the total volume fraction, which is equal to 1 of a body, can we come up with mixture laws that say if I take property number 1 plus property number 2, can I estimate what the overall property is? Overall property by knowing the constituent values of volume fraction of this, volume fraction of this, and the subsequent properties. Can we come up with some design rules? And of course, the answer is yes. This is the backbone of all of composite materials. And the idea there is that by taking these samples of materials, there are certain specialized formulas. They're sometimes called the Hashim-Strickman bounds. And if we go through these procedures, and again, I'm not going to go through this today, you can derive effective property upper and lower bounds for things like the conductivity, the electrical conductivity, the thermal conductivity, the elastic properties. So it's an absolutely beautiful subject. I spent the first 20 years of my career focused only on these problems, and I have to say it was not a dull moment. I have to say it's very rewarding to understand how to mix materials together and to actually produce solids. And it's a pity that we can't meet in person, because usually I bring lumps of clay and I take metallic particles, and then we mix them together in class and make these little samples and then apply some mega magnet to them and show that you can make clay basically magnetic. Because of course, if you add particles to the system, like I'm showing you here, and I take clay and then I add metallic particles to them, even magnetized particles if I like, and then I apply some kind of magnetic field, this overall blob of clay that has these embedded microscale particles behaves like a magnetic piece of clay. And that's a really fascinating thing to understand because, of course, by making these mixtures together, you can use clay, which is really easy to form, and magnets, which are really not easy to form, materials like neodymium that are very, fragile and are very fracture untough. They break rather easily. So usually what happens is we granulate the hard to fabricate material and we embed it in something nice and soft that we can bake. And then effectively we can produce these kinds of materials. In fact, I was just trying to do this today to show someone else of basically taking these blobs of clay that I'm showing you here, different kinds with different properties, and embedding these kinds of metallic particles in this stuff. So it's an easy thing to do. I mean, you can of course do this in your own home, which is pretty easy. You just take a lump of clay or any kind of piece of plastic and start embedding metal flakes into it, and you have immediately then this bizarre metallic composite. And these formulas are able to deliver on exactly what are the overall properties of that stuff. So the purpose of that assignment, which isn't the last one, is simply to say, look, if I have some desired, for example, bulk modulus, and I have my formula that I hope my formula is relatively accurate, I need to somehow figure out how to design the parameters that are in this model. The cost function has, for example, the volume fraction of material 1, the volume fraction of material 2, the bulk modulus of material 1, the bulk modulus of material 2, and so forth. Those parameters dictate everything about how this thing is going to be able to achieve that by messing around with these formulas. So the formulas tell me what the effective property estimate is, and I'm able then to use those formulas to essentially tune the mix, almost like baking a cake or some cookies, that I can figure out exactly what the recipe needs to be to deliver the product I want. And of course, we don't stop at bulk modulus. We also do things like the shear modulus of the material, the electrical conductivity of the material, also the other properties, for example, Poisson ratio. You could do so many different more of them, so it doesn't stop at those. But usually the big three are the elastic properties, which are the bulk and the shear modulus, the electrical conductivity, and then of course the thermal conductivity, which I'll just call here thermal over here as well. So those are usually the big three. So that example in that homework problem, while it doesn't have differential equations, which makes the problem a little bit more difficult to solve, it still has some pretty weighty formulas that you have to be able to stuff into your equations so that you can get something that you can optimize that has all of the different components. For example, the appropriate conductivity, then some constraints on how hot this stuff can get, then the same thing for the thermal behavior and how hot those things can get. And then, for example, things like material mechanical mixtures, which are shown here, which again restrict, number one, not only the bulk and shear modulus that we want, but of course, we have things like this, which are the constraints on how high we want the stresses for the deviatoric and the dilatational part of the material. Again, very clean, a little bit weighty in terms of the formulas, but nothing daunting. But it's good to have had a taste of this in your graduate studies somewhere. And you probably have had some of this already as undergraduates as well. So that was packet 20 and 21. Packet 22, we got into COVID-19. And again, that one is a relatively straightforward problem. Again, there were a lot of different possibilities of what to do. So if we look at packet number 22, packet 22 basically is, an analysis of someone coughs, and we'd like to know where does that stuff go. And as we could see last week, or in fact this week, UC Berkeley has given up on trying to fix the vent systems. I think you've all gotten those emails. So now they are relying on everybody better get vaccinated, because it's quite difficult to control these flow patterns of where these particles will go during some kind of an event like this. So hopefully we'll actually be able to actually see each other in person in the fall. but hopefully we'll all be vaccinated. But this problem still persists because there are other diseases other than COVID-19. There's flu, there's all kinds of things. So it's good to understand what are the physics that control how this stuff goes and how it's controlled by vents and so forth. So that was the main issue of assignment number 22 or packet number 22, was just to give you a taste of the differential equations that go in to modeling this type of stuff and the approximations thereof. You can expect something like that, of course, on the final. So packet 23, 24, 25, way beyond what we could do again, but it gives you more of a taste of what is going on in contact tracing, decontamination, and so forth. So that's basically packets 23 and 24. And then finally, as promised, packet 25, solar farms. And then again, that one, while an interesting problem, as I promised, I can discuss it with you after the class is over sometime this summer if you're interested. And a number of students in my group are working on those kinds of things because I think we all realize that renewable energy now is here to stay, hopefully. And the ideas of exactly how to design those kinds of systems is important. So I've rambled on for about an hour nonstop. I'm happy to have questions, but we can have questions also next week, Tuesday and Thursday. We finished relatively easily, I think, and comfortably, but I don't know, Brian, is there any things you might want to add?
I don't think so.
Oh, maybe if you resend instructions also to do the evaluations. I don't know how they're going there, but the admins and the department nagged me if people could please do their evaluations by, I think, what is it, next Friday or something like that?
I think the final deadline is May 9th on a Sunday, but it seems like from the reminders from the department that they want it sooner, or they're just trying to get people to do it. So
yeah, I think they don't want you to wait till the end of the semester. So if you could do it maybe sometime early next week, if you feel comfortable with that, or at least not by the end of the week, because you never know where there's a system glitch or just you might forget, that would be very much appreciated. Are there any questions on what we have now? Of course, we have plenty of time Tuesday and Thursday for the finals, but is there anything that anyone would like to ask?
it looks like we have a question in the chat.
Oh, okay. All right. Let's see. Let's get to the chat. I can't see it in my screen. Just
I can just repeat my question.
Okay, that would be great. Yeah, go ahead.
So it's not super direct to what we just talked about, but the ventilation system in the school, doesn't that mean that it was like well designed in terms of like good building ventilation? Like, isn't that a good problem to have?
No, the problem is it's not good. It's not well designed. What they have realized is there's really no way to vent out particles in a way that would protect people. So what they've really realized is that trying to guide contaminants or pathogens is probably going to be a hopeless situation for one main reason, Lena, is fire season is also coming. And there is going to be a dilemma that they're going to tell people, stay inside, don't go outside, close your windows. Most of the systems in Berkeley don't have air conditioning, so staying inside with stagnant air that's not being filtered out is exactly the opposite thing you would want to do in COVID-19. You would want to go outside or have fresh air being pumped in all the time. All the studies have shown that if you want to catch COVID-19, sit in a room with somebody for a couple of hours and you'll get it. So the problem is now the dilemma is that California in particular, for those of us that were here last summer, I guess we could also get into this, was that, we were trapped in where you had to have either portable vents to try to keep filtering the system in, but at the same time, you really couldn't go outside. And so the campus has really come to the realization that the vaccines work. So it's not bad news, it's just simply that the vaccines do work. And that's what the health director, Guy Nicolette, who runs the health center for the campus, has indicated that's what they're going to put the chips on now, that they would really like everybody to be vaccinated. And I know that at some schools, I was talking to a colleague of mine at Duke University. He said that even for people to register now, they're asking people to be vaccinated. So you won't even get a chance to log in to register for classes unless you upload a certified vaccination card. Now, of course, there are exceptions for people with medical conditions and things of that sort, because some people can't get the vaccines. That's perfectly understandable. But you have to have some pretty significant proof, as you could see, I think, from some of the messages from campus. I'm never sure which messages all of you are getting as well. I mean, I get all of them as a faculty member. I get the ones that the students get and the ones that the faculty get, but basically are saying that they're about to approve the rules that for anybody to be on campus, regardless staff, faculty, student, they're going to have to be vaccinated, because the vent systems are so heterogeneous. For example, in Echeverry Hall, there is no ventilation system. It's just natural convection. So it's basically the air comes through the windows or the grills. There's nothing that's pumping any air in or out. Whereas if you go to the Citrus building, there is a pretty elaborate ventilation system, because they have all the clean rooms there and they have to have everything pretty hermetically sealed. So there's such a disparity between building to building to building that they've simply, number one, the state has no money to retrofit literally billions of or hundreds of thousands of buildings, which would cost trillions of dollars, or allow people to bring all types of portable vents, because they'll all plug them in simultaneously in every room they're in across the entire campus, which will blow out the circuits. So you're left with really not many options there. Either it's remote instruction forever, which I think we're all realizing is, while has some advantages, is somewhat suboptimal. I'd like to also meet students in person, or have some kind of super vaccine protocol going. And that does seem to be under the Biden administration. It's really taken off quite admirably. So I think that that's the state of affairs.
So, yeah, it clearly doesn't work for the current situation, but it also sounds like in general, yeah, all the buildings are just so different. So some of them might have good ventilation, and others are just like, oh, we'll hope for the best.
Well, so here's really kind of the dilemma too. I mean, there was just so imagine you're sitting in a room and you're over here, you're minding your own business, and your colleague, maybe they're ill or something, they cough, right? So they cough up a storm here, and you're, I don't know, 100 feet away. Under normal circumstances, the person coughs and just drops to the floor, and okay, we social distance and we're fine. The problem is if you have some kind of Uber, ventilation system up here where it's pulling air in, and these vents, in many of the buildings, they're up at the top, they're going to pull this stuff a long way and in fact potentially affect you. So the problem is, unless you say, well, wait a minute, I have to now redo my control system for all these vents to figure out how not for this to happen. But at the same time, that defeats the purpose of what the vent is supposed to do. So you can't really start to tailor all of the different ventilation systems to try to take into account every scenario, because that's just scenario one, person here. What about scenario two, person over here, person up here in the room? If you start to look at all of the different possibilities, and I mean, I believe me, my colleagues at the national labs and I have been working on this nonstop. It seems like there's absolutely no way to control the flow patterns unless it's a super controlled environment, for example, like on an airplane, where you have the vents just all going straight up, and basically you can take the stuff out of harm's way. Beyond that, it's open season. It's better to have open windows, and of course that would be lovely if we didn't have fires, but when the AQI index is 250 outside, putting open the windows is a non-starter. So yeah, each building is so different. I remember the last season when we were actually there during fire season, I guess it was 2019 on around Thanksgiving. The building I'm in, Echeverry Hall, is just a porous sieve. The smoke, whatever the AQI is outside, is the AQI in the building. There's nothing that stops it because it's natural ventilation. So while wonderful when the weather is nice, is a nightmare when the weather is not nice.
Wow.
Yeah, I know.
Cool to know.
Well, I think Berkeley has nice weather, so of course it's never really been much into the air conditioning business, but now we're in a kind of a whole new world, so it's hard to tell what to do. But if you could design the buildings from scratch, which I guess if we were living in a brand new city with brand new floor plans and a lot of money, probably the buildings would be designed in a dramatically different way. But it is what it is now, and we just have to deal with it. Are there any other questions? Well, okay, so have a good evening, and please come prepared on Tuesday, and we'll go through the finals, and we'll get right on that too. And I hope you'll be really, really well prepped for the final, which again, don't stress out about it. It's not a super long one where it takes all week. We're just giving you all week, in the subsequent week, next Sunday, not this upcoming Sunday, but the next one, to have enough time, regardless of your time zones or any of your other personal issues that you might have in terms of timing. You have plenty of time to deal with it. All right.
Thank you.
Have a good evening.
Thank you, Tarek. You as well.
Sure. Bye-bye.
Hi, Brian.
Hi.
So I worked on my code and I made it worse.
Okay.
Yeah.
Might want to stop the recording also.
Oh yeah,
Oh,
that's a good point. I forgot this last time. I forgot this.